Okay, so we're going to finish up with our last set of notes here for Unit 2, and that is on capacitance. And so we've been talking about capacitors sort of indirectly this whole time. So now we're going to talk about them directly. So capacitors, their main purpose is to store energy. What they do is they are basically like the electrical equivalent of springs. All right, when you stretch or compress a spring, what you do is you store energy in that system in the hopes of retrieving it later to convert that stored elastic potential energy, in that case, to some other form of energy, be it kinetic energy or maybe gravitational potential energy or whatever. But it's a way to store energy. So capacitors store electrical energy for use at a future time. I call them electrical suitcases sometimes. So what you can have is you can have a configuration of those parallel plates like we talked about. You can have multiple sets of them in some cases. They don't have to be square or rectangular. They can be any shape that you want. It doesn't matter as long as they're parallel to each other, okay? So what you do is you create a potential difference between the plates, and that potential difference then acts as a way to store energy of the charges. So we charge up the plates, and that is the mechanism that stores the energy. So the work done charging the plates is what causes that. Okay, so when we look at a capacitor, what we think about is how much charge can we store per volt that's across of it? So it's the charge, the total charge on the plates Q, and then the potential difference between the plates, the voltage. So what we do is we charge up one plate, and that induces a charge on the other plate of an equal value, but opposite in sign, okay? So one plate will be essentially positively charged, and the other plate will be negatively charged by an equal magnitude. So what happens is the charging is not linear. The charging takes on an exponential form because at first it's really easy to put charges on the plate because there's nothing there. So the first charge takes no work to move in. The second charge takes a little bit more work, and each successive charge takes more and more work to store on there, so it takes a longer and longer time to get it onto the plate, because we're having more and more charges on that plate, so the charge is reluctant, if you want to think of it that way, to move toward the plate. So the total capacitance of a capacitor is just the total charge on that plate divided by the voltage across, or the potential difference is the same thing between the plates. So it's the charge per volt, and we call that capacitance, and the unit of capacitance is a farad, which is a huge amount of capacitance. So if I have a situation where I can add more charges, then the potential difference will also double. But when I build a capacitor, though, I build it to have a certain value of capacitance, and I can't change that unless I change the configuration of the capacitor. So if capacitance stays constant, if charge changes, voltage has to change. Now, we're going to find out that the capacitance is all about geometry. It's about the physical parameters of the capacitor. How big are the plates? How far apart are they? And what do you put in between them? We really haven't talked about putting anything in between those plates yet. We assumed it was vacuum, but it turns out that you can put stuff in between the plates and actually increase the storage capacity of your capacitor. So it stores more than an empty one does. So it's kind of like the TARDIS in Doctor Who. It's bigger on the inside. So the units of capacitance, as I mentioned, are the farad. 1 farad is a huge volume of capacitance. Normally you see micro or picofarad capacitors, but 1 farad capacitors are huge. They do exist, and they're used in things like car stereo systems. Big, loud car stereo systems have large capacitors, but normally what you see is pico or micro or nanofarad capacitors. Okay, so when I calculate the electric field, if you go back and remember, it's the, when I talked about the electric field between two plates, we saw that it was constant. And what I do is I talked about the charge per area, right? It was the charge per area, which we called sigma, but remember that's total charge over the area of the plate and epsilon naught. So we saw that in the first set of notes. So if I take that and put in for what I just saw for voltage in the previous, just the previous set of notes, I can write down an expression for capacitance, okay? So we have the electric field from the first set of notes. In the second set of notes, we have the expression for voltage that you saw. So let me just replace the electric field in there with what I had in the first set of notes, and I end up with an expression for capacitance that has to do with the physical constant epsilon naught, which is about vacuum being in there. If you put other stuff in there, it has its own value of epsilon. The area of the plates, whatever shape they are, if it's a square or a rectangle or a circle, and then the separation of the plates, D. So once I build it, I have determined its capacitance. Just like when you buy a suitcase, it's the size that it is, okay? It's not gonna suddenly change size because you're putting, you know, shoes in it versus money or something, okay? So the capacitance of a parallel plate capacitor is epsilon naught A over D. And this is true for any parallel plate capacitor. It doesn't have to be square plates. It can be any shaped plates at all. But all capacitors, depending on, you know, it doesn't matter what their configuration is, it's geometry only. It's just a little bit more complicated than this form, and we're not going to look at those. We're just going to acknowledge that they exist. Okay, so when I look at capacitors, sometimes I would like to store more charge on them, because the least amount of charge that I can store is when I have vacuum in between the plates. Because what eventually will happen is the capacitor will get such a large voltage on it that it will sort of overwhelm the capacitor and create a situation called breakdown. And what happens there is, instead of sitting on the plates, the charges instead rush between the plates to try to get attracted to those opposite charges. And that is not what you want. That's called breakdown when that happens, and that means your capacitor has now burned up. Basically, it's shorted itself out. So ideally, you don't want that to happen. But if you want to store a large amount of charge on there, you need to do something to weaken that electric field. And what you do is you introduce a material into the capacitor that's called a dielectric. Okay, dielectrics weaken the electric field in between the plates, and therefore you can put more charges on the plates of the same size capacitor as you had before. Dielectrics are insulating materials, and they basically weaken the electric field, or they kill it off. It dies, dielectric. Okay, so it's some kind of non-conducting material. It can be a lot of different things. Water will work up to a point, glass, Teflon. There's all different kinds of materials you can put in there. But certain things have better properties at weakening the electric field than others. So what the dielectric does is it will increase the capacitance of your capacitor by weakening the electric field. It allows you to store more charge on the plates for the same amount of voltage than a plain capacitor does. So it keeps your dielectric from shorting out, basically, is what happens. It keeps the dielectric from shorting out and passing those charges between the two plates internally, which is not what you want. What you want to do is you want to put the charges on the capacitor and let them sit, and then drain them off through some wire connection on the outside. So if it passes on the inside, you've lost that ability, so you don't want that to happen. Now, so the amount of, if you have, for example, an isolated capacitor and you stick a dielectric in it, if you have it isolated, it can't get any more charges. So what it does is it weakens that field. So the way you can compute it is the dielectric constant. The dielectric constant is a number that you look up. It is not something you know off the top of your head. It's a materials constant that is measured experimentally, and you look it up for the different materials that you might be using. And basically what it is, it's the ratio of the new capacitance with the material to the old capacitance without the material, or other words, with vacuum in there. And that number is going to be 1 or larger. And the larger it is, the greater the capacitance becomes when you put it in there. So what it does when you insert it is it weakens the electric field and it decreases the potential between the plates, because the potential is determined by the electric field. So what that means is I can put more charges on there and bump that potential back up to whatever number I had before I inserted the dielectric. I'll have the same potential, but I'll have a lot more charges on my plates. And sometimes you want that. Now, the dielectric constant is just a number. It doesn't have any units because it's the division of two quantities that have the same units, so the units cancel out. And for vacuum is 1. So that's why we have epsilon naught. And then it causes the electric field to decrease. I mentioned that already. So when we put the dielectric in there, we can rewrite the new capacitance is K times the old capacitance. And so we can replace that in the expression for the parallel plate capacitor, just like that. So what we can do is we can take the dielectric constant, and if we want to, define a new permittivity. In other words, how easy is it for the electric field to pass through this insulating material? That's what permittivity means. So we could actually establish that for whatever material we're talking about. So sometimes you'll see the number written as epsilon, or the permittivity. Sometimes you'll just see it given as the dielectric constant. But either way, you should know how to get to one or the other, depending on what the problem or the book gives you. Now, again, I said the whole point of having these wacky things called capacitors was to store charge, which is effectively storing energy. So we need to know how much energy we can store in a capacitor. All right, so it turns out that it's going to depend on a couple of different scenarios. It depends on whether or not you have it hooked up to a constant voltage or you have it isolated so the charge is constant. But in either case, we're going to find the work done. We're going to find the work done. And remember, work is about the change in potential energy. So we can find it as easily as finding the change in potential energy for each charge that we build up. Now that gets to be a tedious process if you have a lot of charges. But we can just use the expression we developed in the second set of notes about the work is equal to the negative change of potential energy. And if there is initially an uncharged capacitor, it will gradually build up the charges in an exponential fashion. It will also discharge in an exponential fashion. When I hook it up to something and drain those charges off, initially there's going to be a huge burst of charge leave because there's so many of them stored on there. They're pushing each other away. But then as they begin to trickle off, eventually the last few take longer to leave because there's less force on them because there's less charges present. So it's not linear. It's a gradual buildup and a gradual decrease of charge in an exponential fashion. Okay, so we can calculate the energy stored in a variety of different ways, and it depends upon what scenario you have. So all of these expressions basically are the same. I'm just substituting in for different things. So the first expression is 1/2 the charge times the voltage, but maybe I don't know charge and voltage. Maybe I know charge and capacitance. So I use the definition of capacitance to replace voltage and end up with the second one. In the third one, I don't know charge. So I use the definition of capacitance to replace charge. But it depends on what you have. So we're going to look at a little cartoon that will explain that to us in just a second. Okay, so here is a PHYS simulation about capacitors. And so what we've got is we've got a capacitor that is, here are these square parallel plates. Here is a battery hooked up to it. It's hooked up to a constant source of voltage. Okay, I'm going to bring a voltmeter over and hook it up to my capacitor. Right now it registers 0 volts because my battery is basically not engaged. Okay, and so here's this. Now, what I'm going to do is I'm going to take my battery and I'm going to, right now I don't have anything in between here. I just have air or vacuum in here. And as I put this in here, you see what I've got is, as I increase this to plus, I get positive charges lining up on this part of the plate, negative charges lining up on this part of the plate, okay? All right, so, and there's my voltage, okay? So if I increase the number of charges, the voltage increases. Now, what are some other ways that I could increase the voltage? Well, one of the things I can do is I can make my plates, well, I shouldn't say that. If it's hooked up to a battery, its voltage is its voltage. You can't change that. So when I set it on 8.85 volts, I do that. But if I increase the plate area, I can store more charges, okay? I can store more charges because now I have more room and my electric field will get stronger, okay? If I separate my plates though, remember that D value, as that goes up, that increases the voltage. So if I separate my plates by more, I actually have to remove some charges to be able to have the same electric field strength inside there. Okay, now the other thing that I can do is I can remove this. And now what I've done is I've isolated my capacitor. So now what happens, instead of the voltage being constant because it was hooked up to a battery, I have a situation where I can't put any more charges on it. They're stuck, they're marooned there. So now what's going to happen when I increase the plate area, or I go back down, when I decrease the plate area, notice my voltage goes up because now the more charge in a smaller area, I'm increasing my voltage. If I increase my area, they can spread out more and I decrease my voltage. If I separate my plates more, notice the voltage goes up because remember, if I separate the plates, that increases the voltage. Okay, so I can either have a constant voltage scenario being attached to a battery, or I can have a constant charge scenario where I've isolated a charged capacitor. Okay, so now we talked about the capacitance with nothing in there. So here's the same kind of situation, except now we have the possibility to add a dielectric. So I'm going to go ahead and put the things back that I had. This is a little bit different sim, so it's going to look a little different than the one we just used, but they didn't have the dielectric on that one. Okay, so here's the plate charge, and we're going to go ahead and do the capacitance and the stored energy. All right, so right now, if I turn my battery back up, you'll notice it does the same thing as it did before. It has the charges flow onto the plate and it establishes whatever voltage it is. I can move my plate area and that doesn't change my voltage. I can move my separation in and out and that doesn't change my voltage. But what that does change is the capacitance because I'm changing the geometry, and the stored energy and plate charge because I can put different amounts of charges on there. Okay, so let me just go back to right there. Now, so now remember I said that what I could do is if I had a material where I could insert that material into the capacitor, it would change the capacitance by allowing me to put more charges on it. So right now I've got a constant voltage. So if I insert my dielectric right now, like so, notice what happens. I can put a whole lot more charges on here now for the same amount of voltage because it is weakening the electric field inside there. So let me remove that back out. And you'll see that the charge amount drops. Okay, now again, if I disconnect the battery, now I've got a situation where if I change the separation, my voltage changes, remember, because now my charges are isolated. So I'm going to put it back. Now, watch what happens when I insert the dielectric here. Notice that the voltage dropped because now I can't add any more charges. I'm stuck. So the plate charge stayed the same, the capacitance went way up, and then the stored energy went way down because now I have the potential to put a whole lot more charges on here. So you have to know if you have a constant volume, or excuse me, a constant voltage by being hooked up to a battery, or a constant charge by being disconnected from the battery and the charges are stuck. I can change the value of my dielectric if I want to over here, that's allowed. But what it does is it allows me to put this in there and see how there's weaker electric field lines in here for the same amount of charge. The charges are the same, notice, but the field lines get weaker because now the dielectric is weakening or killing off those field lines. So that allows me to put a whole lot more charges on there by upping my capacitance. Okay, so that's just a little demonstration to kind of show you a little bit about capacitance. So that ends this set of notes.